Hello and welcome back to CS300 Introduction to Algorithms. We are talking about data. We have seen so many algorithms so far that process data, different data types, for example, matrices or integers or bits. But at the end of the day, any digital computer is operating on bits only, and all other data types are higher data types in the sense that they are built on bits, or more precisely on sequences of bits. So it's time for us to talk a little bit about these higher data types. And it helps for this purpose to recall the foundations of mathematics that also built up higher and higher mathematical data types, like, for example, real numbers. Real numbers, to think about it, is a very complicated mathematical object. As Kronecker said famously, the natural numbers are made by God. Everything else is the product of humans. And with everything else, he meant, for example, integers, negative numbers, fractions, rational numbers, real numbers, complex numbers, and even higher data types such as analytic functions or smooth functions, integrable function. All these build up mathematically, building onto integers. And computationally, everything is building up from bits. So what is the differences and what is the similarities between these mathematical data types on the one hand and the computational data types? That's what we want to talk about it today. So, and to this end, let me fire up the slides. So the syllabus is the following. We're going to talk about data, about hardware data types, and about mathematical data types, their similarities and their differences. We will talk about abstract data types. We talk about basic data types, Booleans, mathematically. Computationally, these are the bits, the foundation of all computation. Then we talk about integers, which are basically sequence of bits interpreted as a binary encoding. And mathematically, these are the foundation according to Kronecker. And then we talk about higher and derived data types, computational data types such as array of something, queue of something, stack of something. We talk about linked data structures, that is data structures that consists of nodes, which may be basic or derived or any other kind of data structures, and that are equipped and enhanced with some pointers that link the different nodes. That is kind of a computational counterpart to graph data structures, to directed graph data structures. You see the duality really is very similarity is very close between mathematical and computational data structures. Then we talk about data structures that are tailored for particularly efficient algorithm, namely search trees, and in particular balanced search trees. And then we talk about a small relaxation, namely not too unbalanced, but also not strictly balanced trees. These are called AVL trees, and we're going to analyze them. That's our plan for chapter 4. So, and please remember the virtues of computer science. First, problem specification, then the primitives and the semantics and the cost that operate on these data types in order to implement, for example, higher data types on top of a lower one, a hierarchy of higher and higher data types. Then operating on this data by means of algorithms that are designed as opposed to immediately start coding, the analysis of this algorithm, and final virtue, proof of optimality of your algorithm. Otherwise, please start over again and design and analyze a better algorithm. So what's the similarities and difference between hardware and mathematical data types? I'd like to illustrate that issue with an anecdote of my personal youth. When I was in high school, I would play Sid Meier's game of civilization, where the player can choose some country in the world and be the ruler of that country, guided towards a process of gradually becoming a more and more civilized country into the future, while the neighboring countries are played by the computer, unless you have a friend to play with. And the computer plays the neighboring countries by simulating kind of rudimentary artificial intelligence, simulating the rulers of the neighboring countries. And these rulers are described by some parameters. For example, the ruler of India, when played by the computer, is Gandhi, and Gandhi is known as a very peaceful leader, and therefore the parameter describing Gandhi's aggression is 1, very low aggression level. Another rule of the game is that when a country develops democracy through the course of its evolution, then its level of aggression decreases. Democratic countries are less likely to be aggressive or to start a war than countries run by, let's say, dictators. So another rule of the game is when a country over time adopts democracy, then its level of aggression decreases by 2. Now, what happens if when India adopts democracy in such a gameplay? Well, initially the aggression is 1, then reduce the aggression by 2, and the result is, what's the result of 1 minus 2? Well, mathematically, in the mathematical data type of integers, the result is -1. But this game is implemented and run on a computer, and at that time, the basic data type of a computer was a byte, 8 bits. And a byte can store values from 0 to 255. So when 1 is subtracted 2, the result will be 1 minus 1 is 0. Another minus 1 is, there's no way to represent -1 in an unsigned byte. So wraparound occurs, and the result is 255, a very high level of aggression. So that in this playing this game, usually whenever India starts to adopt democracy, Gandhi would start waging war against its neighbors, which is in a game it's kind of funny. In real life, it's a serious bug. So here you see, well, we will mobilize our armies for war. Soon you will pay for your foolish pride, says Gandhi again, according to this game, which is a running gag. But at the end of the day, it's a programming error, right? A programming error because the programmers had mathematical integers in their mind when writing this code. After all, we are all raised and educated thinking in terms of mathematical integers since elementary school, whereas the actual execution using hardware data types was using bytes, which differ from mathematical integers. And this difference is essentially the cause of the difference, the cause of behind the programming error. Or put differently, one way of removing the chance for programming errors is to have computer data types that coincide with the mathematical data types that we're all familiar with. And when there's a difference, a discrepancy between computer and mathematical data types, this is a prone source of errors, coding errors. Now you can think, why not use a signed byte instead of an unsigned byte? Or why not use a word 16-bit or a double word 32-bit? It all helps, but it doesn't resolve the overall problem, because even signed or unsigned double words do have cannot avoid this wraparound effect that mathematical integers simply don't have, right? So, and that's the reason why nowadays in modern high-level programming languages generally offer actual mathematical data types, such as big integer, or in Python it's simply called integers. Of course, these mathematical data types in high-level programming language built on bytes, on sequences of bytes, that is, on sequences of bits that whose lengths are adapted in runtime just to be just long enough so that any possible wraparound is caught and prevented. And that is costly, right? That implementing mathematical integers on bytes is slower than actually operating directly on hardware. But the benefit is, as I said, agreement with mathematical data type prevents lots of programming errors, and the overall slowdown is not that important. It's maybe a factor of 1.2 or 1.5, which is happily paid with nowadays computers being roughly 1,000 times faster than the computers at that time when I was playing Civilization. And this is a cheap exchange of efficiency in return for correct programs. So that's a lesson about hardware versus mathematical data types for integer case. Now let's look at some other data types, both from the perspective of mathematics and from the perspective of computer science. Yes, so we have talked about integers, mathematical data type, and mathematically integers come with operations and with comparison, that is logically speaking a predicate. So we have these operations of addition, subtraction, multiplication, division with rounding or with remainder. We have constants, 0 and 1 are constant integers, and we have this predicate of comparison. And this is what is in model theory called a structure. A structure is a set together with a collection of operations and constants and predicates. In general, there can be several predicates. So this is the structure of integers, mathematically, logically speaking. Another important structure that you're all familiar with is the structure of real numbers. Right, real numbers, what can we do with real numbers? Well, again, there's some constants, 0 and 1, the operations, addition, multiplication, subtraction, and now division without rounding, right? And the predicate, the comparison predicate. So this is an example of a different structure. You're learning model theory here. Anyway, structure of complex number. How does that differ from the structure of real number? It's almost similar. It also has the same arithmetic operation constants, only the predicate is gone, right? As you know, it's impossible to compare two complex numbers because they lie on the complex plane, and one coordinate may be larger and the other coordinate may be smaller. So there's no total order on the complex number that is compatible with the arithmetic operation. Another structure I want to discuss is our rings. And a particular example of a ring is a polynomial ring. Let's say polynomials over real numbers, polynomials over complex numbers. Can also consider polynomial over, let's say, rational numbers. What are the operations that are supported by this structure? Well, it looks pretty much the same as integers, right? We have constant polynomials. There's an additional polynomial like the x polynomial, right? So the linear polynomial. Then we have the arithmetic operations, and we have a division with remainder, right? The remainder, like with integers, it's not like in the real case where we can always divide without remainder. And again, there's no comparison operation, right? No total linear order. And on top, so here we've become more and more complex in the terms of mathematical hierarchy of structures, in the sense that real numbers build on integers. If you remember how real numbers are constructed, maybe you have learned that in your introduction to mathematics course, how complex numbers are built on top of real numbers, polynomials are built on top of real numbers, but everything is in turn built on Booleans, at least computationally. So the Booleans are kind of the simplest data type. Booleans, we have again this constant 0 and 1, and then we have the Boolean operations of conjunction, like an and, disjunction, like an or, negation or not, and then we don't really need a comparison operation because there are only two Booleans anyway, so we're going to skip that. Then continuing towards more complicated or derived structures, the structure of a power set. So if S is a set, then we can form the structure, the power set, to obtain a new set. So this is kind of from axiomatic set theory, Zermelo-Fraenkel, for example. Now, what operations are supported on the power set? Well, we can form the intersection of two sets, of two subsets of S, that is of two elements of the power set. We can form the union of two sets. We can form the complement. And then there are the constants. The empty set is an element of the power set, and the whole set is an element of the power set. So this is what you see here. Constant is the empty set. The entire set is an element of the power set. And we have the operations of intersection, of union, and set theoretic complement. You already see here that there's a certain similarity between this structure and the operation it supports, and the Boolean structure and the operations it supports. And actually, both form what is called a Boolean lattice. It's a Boolean lattice is a structure which supports this operation and that satisfies certain axioms like the De Morgan laws and associativity, distributivity. And whereas a ring is a structure which satisfies basically the properties of polynomials, for example, but there are many more types of rings. So you see that structures are really ubiquitous in mathematics as a way of abstracting from the concrete data we're looking at. Forget that you're looking at whether you're looking at polynomials or at integers, and apply, for example, the greatest common divisor algorithm, Euclid's algorithm, generically. And that's basically an example of information hiding that you all know from computer science, but that has been present in mathematics and logic for decades before computers. Let's look at more structures, shall we? Here's a structure called the Grassmannian, which you may not have heard of, but it's actually pretty simple because you already have attended a course on linear algebra. And in linear algebra, consider V to be a vector space. Let's say Euclidean vector space, that is with an orthogonal complement operation. Then we can consider the set of all subspaces. Okay, consider the set of all collection of all linear subspaces. Let's make this graphic, shall we? Let's consider the Euclidean space of three-dimensional Euclidean space of this room, this office or your room. Okay, it's three-dimensional. Okay, no Einstein relativity going on in your at least in my office. There's no relativity distortion. So three-dimensional Euclidean space. And what are the linear subspaces? Well, for example, they're rays emerging from the origin. One corner of my office is the origin, and their rays are emerging from this corner into all possible directions, and these are one-dimensional linear subspaces. Then there may be planes emerging from that corner. Planes are all two-dimensional linear subspaces. And then there's the full space, the whole office as a three-dimensional subspace of itself. And then there's a trivial subspace that only consists of the origin, the corner, the one single point. And this is a collection of all linear subspaces. And this is what is known in mathematics as the Grassmannian, the collection of all these linear subspaces, but equipped with certain operations. And what can we do? We can form the intersection of two linear subspaces to gain or obtain another linear subspace. So intersection of linear subspaces is another linear subspace, and that's an operation on the Grassmannian. Union of two subspaces is not again a subspace in general, right? So if you consider the union of two rays, then there is an angle between the two rays, in general, a gap, and so it's not a linear subspace, but the Minkowski sum, the set of sums of elements from one ray and add any element from the other ray, that's again a linear subspace. The Minkowski sum of two subspaces, the pointwise sum of two subspaces, is again a subspace. Another operation on the Grassmannian. And finally, there's the orthogonal complement operation. So if you consider some ray here, then its orthogonal complement is a plane, the plane perpendicular to that ray. Try to imagine that in your mind. I don't have that right now visible in my office, but it's there. And dually, the orthogonal complement of a plane is a ray, is a line, so that the Grassmannian as a structure, abstract structure, forget all the graphical geometric representation, just algebraically has the operations of intersection, right? Intersection of two linear subspaces. Then there's the Minkowski sum indicated here. Then there's orthogonal complement indicated here. And then there's the constant. The whole space is a space, a linear subspace of itself. And the trivial space consisting only of the origin is also a linear subspace, a trivial one. And here, let me emphasize again the similarity to the power set, right? We have the intersection operation, but the union operation is now replaced by the Minkowski sum. Set theoretic complement is replaced by orthogonal complement. Whole set is here. The empty set is replaced by the trivial subspace. And we already said that the power set is similar to the Booleans. So what is the difference between the Grassmannian, which also forms a lattice, a complemented lattice, to the power set and to the Booleans? The difference is that there's no distributive law in general valid in the Grassmannian, but there's a weaker law. But that leads to quantum logic and to lattice theory, which is far beyond what we want to discuss here. The message to take away here from is that all these are examples of structures, sets with operations, very similar operations, and there are only some small differences in their axiomatization. This here satisfies the distributives, the De Morgan laws. This here does, but this here does not. Also want to talk about a variant of the integers, which is known as Pressburger integers. Namely, that's the same set of integers, so the set is the same, but one operation is simply dropped, or actually two are dropped, namely multiplication and division. So in Pressburger integers, we can only add and subtract and compare, but you cannot multiply or divide. So that's an example of what is called a reduct. Reduct means forget some of the operation. And really what we see here is this very strong similarity between mathematical data type and abstract data types in computer science, right? So if you imagine these are all objects, right? Objects in object-oriented programming with operations, and some have these operations, and some have these operations, and some operations satisfy the distributive laws, others don't. Here we have dropped some operations, so it's really very similar to object-oriented programming and abstract data types. So the meta definition borrowed here from mathematical logic is that a structure is a set equipped with some operations, that means functions, some constants. Constants are basically also functions, just zero array functions, right? These are, here we have binary functions. Here we have some unary function. Complement is unary. Addition and intersection are binary. And we have some relations, that is predicates. So now you already have a starting background in logic and model theory. And axioms are simply mathematical propositions that are satisfied by the structure, such as, for example, the distributive law, or they may not be satisfied, in which case they're not an axiom. For example, the distributive law is not an axiom of the Grassmannian, but one of the power set. And this is similar to abstract data types, which are also hide the particular implementation, but emphasize only axiomatically the properties exhibited by the operations axiomatized. So, structures which satisfy certain of these axioms are kind of combined, summarized. For example, group is a structure that provides some operation and some constants that satisfy the associative law. A ring is a structure that provides some operation and satisfies some axioms. This is also an example of a ring. And we have some field. It's a type of structure. And we have lattices here. So these are kind of classes or types of structures satisfying certain axioms. And yes, as I kept emphasizing the similarity between logical and computer data types, and also the differences, like the wraparound effect of bytes and words compared to the lack of wraparound of mathematical integers. Let's have a look at the data types of integer. As I already said, in modern high-level languages already support that natively, and if it doesn't, then you can always just include the GNU multi-precision library, which then by importing provides such a pure mathematical integers. Booleans and bits are the basic data type of any digital computer. That is what everything operates on, way down below. But real numbers is, and I have to say that because that's my own area of research, real numbers mathematically, on the other hand, computationally are commonly represented by floating point numbers, and floating point numbers are, like bytes and words, are hardware data types. Since 1985 standardization by the IEEE standard, they are not real numbers, they are different. And like the programming error in the computer game Civilization arose from the discrepancy between mathematical and hardware data type, similarly numerical programs easily exhibit errors from the discrepancy between mathematical real numbers and hardware floating point numbers. And this is a common source of inaccuracies in numerical programs, and it takes both a skilled programmer and a mathematical analyst to bound and to estimate the effect of such discrepancy, right? Same as the discrepancy between bytes and integers in Civilization. And what we're doing in this lab is we're actually providing real numbers as exact data type, and people don't believe me, but this is possible. It is possible to have real numbers, not just algebraic numbers, not just rational numbers, but real numbers implemented on a computer. And how to do that, that's an entire different story that goes far beyond the purpose of this lecture. I have uploaded an entire lecture series, CS300, on YouTube on how to do that and how to study algorithm design and analysis in this setting. But this is a kind of a opportunity for some cross promotion, and I'll leave it at that and move on to continue emphasizing the duality between abstract data types in computer science and mathematics, where axioms describe their behavior regardless of implementation, right? So, for example, you can imagine integers to be implemented in various different ways, and in particular, integer multiplication can be implemented in various ways. Remember, long multiplication, Karatsuba, Thom, Cook. These are all ways of implementing real number integer multiplication, multiplication of integers of arbitrary long sequence of bytes with different efficiency, but user program can and will build on that and just multiply two integers and depend and rely that the result will be correct. And now we're moving on to derived abstract data types, like, for example, a stack of X, where X is some, in turn, some either basic or some abstract or some derived data type. And there you can imagine various ways of implementing a stack That's I don't want to go into detail, but the operations supported by this derived data structures is, for example, new, create an empty stack, push an element onto the top of the step, pop the top of the stack and return its content, and predicate whether the stack is empty. And you see, this is really in close correspondence to the mathematical structure, right? New corresponds to constant because it returns kind of an empty stack, right? Push takes a stack and takes an element and puts that element on top of the step and returns a new stack, which now has that element on top of. So that's kind of a operation, a mapping from the stack and with the element X to the data type stack. Pop is an operation that takes a stack and returns both a modified stack, now with the top element and the top element itself. And this is a predicate corresponding to this. So it's really, really very similar. Same for the Q abstract derived data type. Here only the operations differ. There's still a new operation like corresponding to the constant. There's an operation NQ an element, add an element to the Q, DQ an element, remove an element from the front of the, right? So the stack, stack is also known as LIFO, right? Last in, first out. What has been pushed on top, and the next pushed, the next pop will remove that last in, will first out. Q, on the other hand, is also known as a FIFO, first in, first out. And so the axioms of these operations is different. For example, pop of push is the identity, whereas DQ of NQ is not the identity. So it's a different axiomatization. Yes, here, as I said, for LIFO, pop concatenated with push is the identity, whereas this is a FIFO. Now we've thus talked about structures, both mathematical and computer science data types. I should also emphasize that, like in mathematics, one can kind of combine these data types, right? So, for example, common higher data type in mathematics is like vector or matrix, right? Matrix of Booleans, matrix of integers, matrix of real numbers, matrix of complex numbers, or matrix of vectors, where every entry is a vector, or matrix of matrices. This is what is known as block matrices. Matrix of functions, or functions of matrices. So higher and higher data types are everywhere common in mathematics, and similarly in computer science. You can think of a stack of integer, right? Or a stack of Boolean, but you can even think of a stack of stacks, where everything element on the stack is in turn a stack. Or you can think of a stack of queues, a queue of stacks, and so on. Stack of arrays, array of stacks. Yeah, whether this is useful or not, and in which cases this is a different question. What I now want to talk about is the computational cost of these data structures, and specifically that means the computational cost of the algorithms that implement these operations, right? So here we talk, for example, about a conjunction, AND operation, a disjunction, OR operation, negation, complement operation, addition, subtraction, multiplication, division on integers, push, pop, test whether it's empty or not, right? So all these operations, the part of the information hiding is that the user does not need and must not know how it's implemented, but still the user wants, of course, these operations to be run as fast as possible, right? And how fast is that possible? And in computer, you can think of it as a digital computers where all these operations here on bits are feasible in constant time. operating on 1 or 2 bits, that takes constant time. And more generally, operating on a constant number of bits, like on 8 bits on a byte, takes longer, but still constant time. Operating on 32 bits, 4 bytes, it takes even longer, but still constant time. When the asymptotic starts to kick in, when the number of bits, the length of the bit sequence starts to grow over the course of operation, this is exactly what happens with integers, right? Integers are not native objects for a computer to operate in. Instead, computer uses binary representation sequences of bit to implement and operate on on integers. And here the running time grows with the length of the integer, and we've spent a great deal of time discussing implementations for integer well, to be fair, we talked about polynomial multiplication, but this is basically the same. So addition, for example, of integers runs in time, which is linear in the binary length, which we use with the letter n to denote the binary length. And as you recall, binary length is asymptotically the same as a logarithm of the value, right? So don't confuse binary length with value as complexity parameter. And we spent some effort finding efficient algorithms for multiplication. We talked about a quadratic long multiplication. We talked about a subquadratic Tomb, Cook, and the fastest known algorithm here is the one due to Martin Führer, which is far too involved to present or not even mention, analyze its computational cost. But the long story short, this can be done using n log n asymptotically operations on bits. So now talking about higher and derived data types like array, and there are kind of two types of arrays, static and dynamic arrays. Let's first talk about static. What are the operations supported here? Here's the operation that means access, right? So given an integer index, read or write the corresponding element at that position, return the size of the array, which is trivial if it's a static array, but interesting, it's a dynamic. If it's dynamic, then there's a resize operation supported, and maybe there's a even higher operation search supported. Otherwise, you can or maybe are supposed to implement the search yourself by repeatedly accessing elements in order. So also this array fit into this paradigm of computing coming from model theory and structures. And the common conception is that array access has constant time, although that is something whose realism is to be discussed, but not in this lecture in introduction. Searching then takes linear time unless it's a sorted array, which brings us to the next data type, which is sorted array of Y, with the hypothesis that Y is a totally ordered set, whereas X can be any set, any structure, any data type, right? You can think of an array of stacks. You can think of an array of queues, but you cannot think of a sorted array of stacks or sorted array of queues. So here the hypothesis is, or requirement is, that Y is totally ordered. And then the operations are search, insert an element, and to delete an element. And these incur running times like logarithmic, when we can do binary search here, right? On the other hand, inserting is very costly and deleting is very costly, because it requires removing and moving large parts of the array up and down. So that's an array. What we're going to talk about later is more efficient data types that allow for search and insert and delete in logarithmic time, right? So you see here, this is clearly the bottleneck of a sorted array, right? This is fast, but this is slow. Here's the opposite, right? Here, inserting and deleting in a dynamic unsorted array is fast, but searching is slow. Here it's the opposite. It's inserting and deleting is slow, but searching is fast. And we want, of course, data type that supports all these operations in hopefully logarithmic time. And this is achieved by a priority queue. And due to information hiding, the user must not know and must not depend on how such a priority queue is implemented. We discuss one way of implementing it later using AVL trees, but the operations supported by a priority queue are find the minimum element and insert an element both in the optimal logarithmic time. So to summarize, now we have seen many mathematical and computational data types, all climbing from basic to higher to derived data types. These can be iterated and combined, but the additional flavor added from the computer science perspective is about the computational cost of the operations that are also present in mathematical data types and structures in different ways of implementing these operations. That's what algorithm design essentially is about, and that's what all we've discussed in the first few chapters now comes into place in this puzzle as particular examples of operations on such abstract data types implemented as efficiently as possible, such as, for example, multiplication of integers or polynomials, which spend a lot of time about that, right? So this now you have the general picture of how all these ad hoc algorithms, seemingly ad hoc algorithms, fit into much larger general picture that originally actually comes from mathematical logic. Okay, so how can we implement more efficient data structures than the arrays that I just said, for example, in order to realize a priority queue? And the key to that is linked data structures. So what you see here is a very basic example of a linked data structure. Namely, the data structure where the basic data type is just integers. The integers you see here are natural numbers, as a matter of fact, right? But these are enhanced and equipped with additional elements, namely pointers. In this case, pointers to the next and pointers to the previous element in the list. Next and previous, next and previous. And this is an indicator that we've reached the start of the list and we've reached the end of the list. This is called a sentinel sometimes. So this is an example of a doubly linked list. And as you can see, it doesn't really matter what is stored in these elements. Here it's natural numbers, but it could be anything. It could be floating point numbers. It could be matrices of queues of files or whatever. So this is kind of a generic derived higher type of data structure. And the one way of using that is, for example, in order to implement a dynamic array. But here in this way of implementing dynamic array, random access is very slow because we have to really walk through the entire list in order to find or even access a certain element, unless we have an external pointer directly maybe to the element 737, then there's no need to traverse the entire list. So first example for linked data structure where insertion and deletion is feasible in constant time, simply redirect the pointers, right? So that's important in an array. In order to insert and delete something, we really have to shift the entire array content, which can easily incur linear cost. But in a list, we only need to redirect pointers and not move. So that means changing or moving a constant amount of portion of the data, namely changing the pointers. On the other hand, the disadvantage is that searching or any other kind of access incurs linear cost running through the list until the element is found, which could, in the worst case, be a large portion of this list. More general, a linked data structure you see here on the bottom. Maybe this is a directed graph, mathematically speaking, but the computer scientists of you already see that this is simply just a linked data structure with one unidirected arrows, right? From here to here to here to here to here to here. And mathematically speaking, this is directed, but not acyclic graph. You see, the graph has a cycle here, right? Which is perfectly fine as a data structure. The question is, what is the purpose of such a data structure? But the generalization compared to here, this is a linear list. Every element has a predecessor and a successor, but here it's not linear because this element has two successors. This has no successor at all. It's not a tree either. It's just a directed graph. If we want to have an undirected graph, one way is to add for every pointer also a pointer into the opposite direction. And we'll talk more about directed and undirected graph as sources of computational problems, graph algorithms in chapter 5. But here we consider graphs more as data structures, as tools. Okay, let me say that again. Here we consider graphs as computational tools for data structures, and later we're going to consider graph as sources of computational problems, graph problems. So a special kind of such directed graph is a directed acyclic graph, which is also known as a tree, and mathematically and computationally it corresponds to such a tree data structure as you see here, which has a root. It's a rooted tree, and it has leaves that have no successors, and then their internal nodes. And this is a common type of data structure. Again, let me emphasize that here the number of successors varies from 1 to up to 3 here, right? So here the number of links is constant, which corresponds to the degree of the graph. So this is the constant degree graph, but here this is not a constant degree graph because the degree, it's not a regular graph. That's the terminology. So let's talk a little bit about tree data structures that you're all probably familiar with. Various trees, binary trees or regular trees that have where every node either has 2 successors or none if it's a leaf. Here you see such an example, and there's also an exception. Maybe some internal nodes may have only 1 successor. So 0, 1, or 2 successors for each node. That's a binary tree. And a binary tree is a binary search tree if it satisfies the additional properties that at every single node, all elements in its left subtree are smaller and all elements in its right subtree are larger. Let's verify that this is the case here. Let's consider the root. All elements in the left subtree of the root have value less than the value in the root, and all your value entries on the right value is strictly larger than in the root. And the operations thus supported by a binary search tree are, as it's called, a search, insert, and delete. So let's talk about the generic implementation of search, insert, and delete in the binary search tree. In order to search an element, let's say we want to search the element 4, then we start, our algorithm starts at the root and checks that the value we're looking for, number 4, is less than the value in the root, namely 8. So the algorithm will proceed into the left subtree, harnessing the promise that all elements in the left subtree are those that are smaller than 8. Then we do another comparison with this new, now with this as root. Our value 4 is strictly larger than this value. So the algorithm will proceed into the right subtree again, harnessing the property that also in subtrees, all elements larger than the root value are to the right of this root value. Another comparison means we now must proceed to the left again, and here we are and have found the element 4. So that's a generic algorithm for binary search in binary search trees, harnessing the promise property that in each subtree, the elements smaller than the root are to the left, and the elements larger than the root are to the right. And if we're looking, let's say, for the element 5, then there would be another step, namely, this is not 5, so we would perform another comparison to proceed to the right subtree, but there is no right subtree. And then the algorithm will report that 5 is not at all present in this binary search tree. That can also happen. Similarly, insert proceeds in a similar way. If we want to insert 5, we walk down the tree in the standard fashion as we just did. But now recognizing that 5 is not in the tree, we will insert, we will add 5 as a new leaf to the right of 4, to the right, because 5 is larger than 4. So this is how to insert elements into the tree by first performing a search and then inserting a new leaf. And dually, deletion works by first searching the element. Let's say we first search 4, and then pruning the corresponding leaf. If it's a leaf, if it's some internal node like 6, we remove 6 and then choose either of its two neighbors, its two successors, to become the new root. Let's say moving 7 up here to replace 6, and thus avoid creating a gap, a hole in this tree data structure. So baseline search, insert, and delete basically all work the same way in this binary search trees, but we have not yet analyzed the computational cost of these generic algorithms: search, insert, and delete. And indeed, the computational cost depends on the shape of the binary search tree, and more specifically, it depends on the depth, so also called height. So search, insert, and delete in a binary search tree takes a number of operations that is proportional to the height of the tree, because we move down in each iteration, we move down the tree by 1 level, right? Until we either hit a leaf, and then we either report the element not found, or we have found the element, or we insert an element at the leaf, or we delete an element from the leaf. But the problem is that the height of a binary search tree can be very large. It can be as large as the number n of elements in the tree. This is an example of what is called a degenerate tree, right? So here you see an example of a degenerate tree. It's a search tree, right? Every node has this promised property that all elements to its right are larger than the root node. But the height is it's not at all a balanced search tree. So that the time for searching or inserting or deleting in such a degenerate tree is actually the worst of all array data structure. Searching in linear time, inserting in linear time, deleting in linear time. We don't need such a sophisticated data structure to get such bad running times, right? We can do that right away on an array much easier. On the other hand, how about balanced search tree? That seems like a good idea, right? Balanced search trees, binary search tree. I mean, what is the depth of the optimal depth? What can we expect as a depth of a binary tree? So this is a degenerate one. This is a worst case where the depth or height is linear in the number of elements. But the best case is where the depth is logarithmic in the number of elements. And this is best possible. One cannot beat that because simple induction shows that any binary tree of height h has at most 2 to the h plus 1 minus 1 elements. And we say that again, if you have a binary search tree of height h, then let's say the case h is equal to 0. That means we have just a single root. And then this evaluates to 2 to the 1 minus 1, that's 1. Indeed, so a single root has height of height 0 has 1 element. And then I'll leave it to you to perform some structural induction, taking into account that a binary search tree of positive height larger than 0 consists of a root and 2 binary search trees as children of height and h minus 1. So that's the induction step. And that allows you to easily prove that inequality, which then solve for h means that h is at least logarithmic in n. So that's the best case. This is kind of the both extremes. Linear height is the worst case, degenerate. Logarithmic height is the best case. But how can we maintain this best case? How can we, that's the hardest part. Even once a perfectly balanced optimal binary search tree has been constructed, which comes close to this optimum, then over a sequence of insert and delete operations, search doesn't change anything, right? But insert will increase the height. Insert will append an element at the as a leaf, and thus increase the height. And delete, if done badly, will fail to decrease the height, right? So it may maybe this is the dominating the leaf that dominates the height, but maybe this one gets deleted, then a delete operation may fail to reduce the height, although it perhaps could. So the difficulty is really maintaining a balance, because maintaining balance itself can become very costly. And there we have this trade-off, right? On the one hand, we want balanced trees, which have height as close as possible to logarithmic in the number of elements. On the other hand, maintaining that throughout insert, that makes search fast, but maintaining that throughout insert and delete operations kind of deletes or can spoil this property, and maintaining it in turn can turn out to be more costly than what is gained. And so this trade-off, keeping this optimum while not spending too much effort on rebalancing and insertion and deletion, that's kind of a challenge of balanced binary search tree. So balanced binary search tree is one whose height is close to the optimum, or we can impose different conditions, stronger and weaker conditions. So one is a perfect binary tree, where every single node either has 2 or none successors, right? And now this is actually called a full binary tree. Here in a full binary tree, every node has here either 0 successors, in case it's a leaf, or no successors, in case it's an internal node. So that's a full binary tree. This is not a full binary tree because here this node has only 1 successor, but it's a complete binary tree because, well, that's the best one can hope for if we have 6 elements, like in this case, right? With 6 elements, there has to be some, for parity reasons, some node must have only 1 successor. And a perfect binary tree, that's of course perfect, as the name suggests, but perfect binary trees will only have a number of nodes that are of this form, 2 to the h plus 1 minus 1. So here with 7 elements, there exists a perfect binary tree, but with 6 elements, there doesn't even exist one. So we cannot hope for perfect binary trees, but we can hope for full or for complete. But maintaining this property, as I said, it can become very costly. So here's an example. So here we start with a perfect binary tree, right? This is perfect. And now imagine inserting 15, right? 15. Inserting 15, you see the search tree property is satisfied. Go to the right, go to the right. At 15, now the height has increased. Yeah, but that's unavoidable, right? But now suppose that the next operation to be performed that the user requests is delete 0. So then we delete 0, and now the balance gradually starts to decay, right? Because now here we have over too much, right? So now we're back at having a perfect number of nodes, but now the tree is not perfectly a perfect tree anymore, right? Right. So there exists perfect trees of having 7 nodes. There exists perfect trees having 15 nodes. Here we have inserted and deleted an element, so we're back to 50 nodes, but the tree is not perfect anymore. Rebalancing, that's the lesson to be learned from here, is rebalancing is costly, and we need to strike a kind of balance between the computational cost of rebalancing and the computational cost of maintaining bounded depth close to logarithmic. And the answer to this trade-off, or one very famous answer, are AVL tree, named after Adelson Belsky Landis, who invented this in 1962. AVL tree, I will repeat this next time. But let me introduce it right now. First, AVL tree is a binary tree, not necessarily a search tree, but with a condition that left and right subtrees may have height difference at most 1 at every single internal node. So that's kind of a structurally inductive definition. For the root, it must hold that for the root, the left and right subtree must have height differ at most 1. So at 1 can be larger by at 1 or smaller by at 1. And the same must hold true for every internal subtree, for every internal node, which is considered again as a root of a subtree. Here you see some examples, right? So for example, here T2, this root here has 2 subtrees, the left subtree of height 2, right subtree of height 1, difference is at most 1. Same here, the root, this subtree is 1 deeper than the right subtree. And the same holds for this subtree, because this subtree here is basically the one here that we've already verified, and so on. So this is our introduction to AVL trees, and we'll say much more about AVL trees and analyze their depth and the operations to be performed on AVL trees when using this as search trees, the rebalancing left and right rotations next time. So for now, that's all. Thank you very much for your attention, and see you next time.